Hi all, my name is Michael, and I'm going to briefly introduce our paper. So our main result is that the problem of recognizing whether a given monadic syrup is bounded or first order rewritable is 2x time complete. So what are these monadic syrups and why the problem is interesting? A monadic syrup is a data log program with a single recursive rule, which defines a unary predicate, like in this case, and some non-recursive initialization rules, like this one. And this syrup finds the nodes that are reachable from given source nodes are in a given hypergraph. So the hypergraph is given by its hyper edges. Can we optimize programs like this by removing or simplifying recursion? Is it possible to convert, to equivalently rewrite the syrup into an equivalent first order query? Well, not in this case, because evaluating this syrup is polynomially is p-time complete, that is beyond the capabilities of first order logic. This optimization problem has been investigated by the database community since approximately mid-80s, with both positive and negative outcomes. For example, there is a complete classification of binary chain syrups by Afrati and Papadimitriou. On the other hand, Marcinkovsky proved that deciding first order rewritability of ternary syrups is undecidable. But Kosmodakis and co-authors show that boundedness here of monadic data log programs is or can be done in double exponential time. Almost 30 years later, Benedict et al. Established a matching lower bound for monadic data log programs with multiple rules. However, the exact complexity of deciding first order rewritability of monadic syrups with one recursive rule has remained open so far. It's somewhere between NP and 2x time. And now we finally settle this 30-year-old open problem. Benedict et al. Showed 2x time hardness of deciding for rewritability of monadic multi-rule data log programs by first using the fact that double exponential time is the same as alternating exponential space. And then by encoding alternating Turing machine computations by annotated binary trees in a way originally suggested, I guess, by Björklund and others in 2008. Multiple rules in the program were used to make sure that the alternating machine rejects the input and that its computation is encoded correctly. Each rule checks defects, errors of a particular type, and it also checks the presence of a rejecting configuration. We use the same master problem, but as the first innovation in our proof, we developed an encoding of computations that allows a simpler annotation of binary trees. We call them 0-1 trees, the only extra information is memorizing which is which of the at most 2 children of each node. With the help of this, we prove the tight lower bound for monadic syrups of the following very simple form. Yeah, they have one initialization rule, this one, and one recursive rule, with 2 IDBPs here in the body, monadic, and also with one EDB, A, and several possibly EDB T, like here. And this part Q is a set of edges that form a directed acyclic graph. We call syrups of this kind 2 syrups. A classical criterion of for rewritability of data log queries works like this. We construct expansions of our syrup by taking first the initialized body of the recursive rule, like here, and then recursively replacing this T0 and T1 nodes by the same body, like this, keeping X well on top. According to Norton's general criterion, the syrup is therefore rewritable if and only if every expansion contains a root preserving homomorphic image of some expansion with bounded depth of recursion. So we cut the number of recursions to some fixed number. In this case, a disjunction of all of this expansion till this bounded recursion depth is enough for rewriting of the given syrup. X is the only answer variable, all others are existentially quantified. Now, in 2 syrups, we always have 2 ways of expanding, the left T or the right T. We can encode them by 0 and 1. And this makes it possible to represent not only Turing machines, but expansions of 2 syrups by 0-1 trees. And this is the second innovation of our proof. We connect 2 syrups with alternating Turing machines via 0-1 trees as following. Given an ATM M using exponential space on some input, we construct a polynomial size 2 syrups, this sigma q, such that M rejects the input if and only if the expansions of the syrup satisfy the criterion of FO rewritability. As the computations of the machine are represented by 0-1 trees, detecting the presence of a rejecting configuration or defects, errors in the encoding can be done by polynomially many polynomial size Boolean functions, each gathering input from some small polynomial size neighborhood. For each such function f, we include an so-called f gadget into this queue here. And this is the third innovation in our proof, namely the uniform design of gadgets implementing these Boolean functions. Each gadget is supposed to force homomorphism of a certain kind, mapping into every large depth expansion a small depth cut of itself. And note that this bound on the depth of recursion actually can be huge. In fact, it follows from our construction that the FO, in fact, UCQ rewriting on the previous slide can be of doubly exponential size. We obtained actually our main result as a byproduct while trying to classify monadic disjunctive data log syrups by their data complexity. A D-disjunctive syrup is a primitive program like this with a conjunctive query Q having the form of a labeled graph. Yeah, and it's mediated by this covering axiom. For example, a D-Sirup can check whether in an, say, incomplete database, there is a postgraduate student mentoring and an undergrad who is in love with a postgrad. Yeah, of course, here we need the background knowledge represented by this axiom. These syrups can be regarded as a very basic type of queries and ontology-mediated data access, yeah, or virtual knowledge graphs, yeah, with description logic, which is a hot area since 2005, where the key practical notion is first order rewritability. Deciding for rewritability for monadic disjunctive data log queries or description logic ontologies is pretty hard, as shown by Benvenute and Carter Lutz, Walter, and co-authors. Now, we are interested in the syrups because they look primitive. Yeah, these little things, and yeah, they capture many fundamental difficulties of the general case. Yeah, they cover all the relevant complexity classes, as the examples below show, or they can have exponential size resolution proofs only. We prove that deciding for rewritability of this syrups is too extra hard. But on the other hand, we also show that positive and non-trivial explicit classifications of some natural classes of graphs, say for Q, for this D-Sirups, say path-shaped queues or directed tree-shaped queues, yeah, these results are possible. And obtaining such possibly partial explicit classifications and dichotomies, coin P, V, P, V, NL, and so on, I think this is the main theoretical challenge in this area. Yeah? It's a kind of a variant of classifying constraint satisfaction problems. On the other hand, advances in this direction can be utilized in virtual knowledge graph systems, yeah, whose ontology languages at the moment are rather limited. Thank you.